Well, the theory of computation goes back to Alan Turing and his famous 1935 paper in which he introduced the first mathematical model of a computer, and this is well before computers actually existed. And so he made a definition of what a problem can and cannot be solved at all by a computer. But if it can be solved, the problem was it might take billions of years. So then in the 1960s, we had the complexity theory coming in, and Jack Edmonds in the 1960s introduced two classes, P and NP. And P stands for polynomial time, NP is non-deterministic polynomial time. And P is supposed to be the classes that can be solved feasibly in practice, and NP they may or may not be, but it seems to be a much broader class. My contribution in 1971 was to introduce the notion of NP completeness, and a problem in NP complete, if it's in NP, which doesn't necessarily mean it's hard, because it could be in P, for example, or it could have an easy algorithm. But if you could solve an NP complete problem, then it turns out that every NP problem could be in P, and we just don't think that's true. And so showing a problem is NP complete shows in practice you're not going to find a feasible solution for it. That's okay. What's the significance of my problem? The point is that showing a problem is NP complete suggests very strongly that there's not going to be a computer program that solves it efficiently, although in practice it can be solved, but it may take forever, billions of years. And the reason it turned out to be important is that it turns out there are thousands of known NP complete problems. I didn't show them. My successors showed that a great many very important practical problems are NP complete. And the significance of that is don't waste your time trying to solve a universal program that does it efficiently. Instead, you just try to cut corners, find an approximation, or work around it somehow. Okay, it's an interesting question. Of course, whether P equals NP is one of the main open questions in mathematics. If it turns out that P equals NP, which would be a surprise, then every one of these supposedly hard problems would be in P, and so what would be the effect of that? Well, it's not clear. For example, cryptography. Many cryptographic protocols depend for their soundness on the assumption that P is not equal to NP. So it might have very interesting effects on the real world if it happens. So the question is, am I working on the problem, does P equals NP? And the answer is no. Years ago, I spent a lot of time working on it, but I now realize it's extremely difficult. There are mathematicians, very bright ones, working on the problem, but they just haven't gotten very far. I'm convinced it's a very difficult problem, and it's going to be years before it's resolved.